Morning, everyone. So we're going to continue on with our wave optics section. Up to this point, we've been focusing on mirrors. Mirrors are an optical device that mainly deal with reflection. Basically, light waves, they hit the shiny surface of the mirror, and they reflect back, they bounce back into the same medium. We saw a couple examples of where our brain just plays tricks on us, where if we see light rays coming with a certain trajectory, our brain just interprets it as if it had come from some virtual images actually behind the mirror. Remember, again, behind the mirror doesn't physically mean you're walking around the mirror. It means you're still looking at the shininess of the mirror surface, and it's almost like there's a whole flipped world inside the shininess of the mirror. And we took a look at how ray diagrams, how light waves here, they interact with these optical devices, mirrors and lenses, in order to predict where images are going to appear. What I want to do in this lesson here is I just want to sum up for you some of the ray diagrams for the mirrors we've seen so far, and I want to switch over to do ray diagrams for lenses. So let's have a look first at just recap from previous. We're going to have a look at mirrors. Mirrors, again, just keep in the back of your mind here, mirrors do reflection for us. Mirrors make light waves bounce backwards. In this case here, we're going to start off with our first type of mirror, which was called a plane mirror, a flat mirror. Again, the word plane just means a flat mirror. And this is the one that you're probably most used to inside your homes, are probably these flat mirrors. Basically, there's no real surprise to this. If I were standing in front of this flat mirror here, we had defined some terms. U are always called the object. We had defined a DO. DO was sort of the distance of the object. We had defined an HO, the height of the object. Because this is a perfectly flat mirror, again, just for simplicity, I just sort of draw light rays as emitting from you. But in reality, what's actually happening is your light sources, maybe the lights in your room are sort of at the top of your room, or maybe it's the sunshine, whatever. Realistically, the light rays are actually bouncing off from the sun and bouncing to you. But what we're interpreting here is sort of the leftover light waves that sort of head towards us. So here we are looking at the shininess of the mirror. And what's ending up going to happen, because this mirror is perfectly flat, because of the angle in equals angle out, our brain interprets, if there's a light ray that's coming directly for us, it interprets it as if it had come from behind the scenes. So what it ends up generating for us here is called a virtual image. This is the image that's inside the mirror itself. We call this one here the image. The distance to the image here, we can call it a DI. The height of the image here is HI. For a plane mirror, because everything is perfectly flat, the DO is going to equal to the DI, and the HO is equal to the HI. So basically, everything is a perfect mirror image. Really useful when you're like getting ready in the morning. You want to be able to see yourself clearly. You don't want your image to be in any way obscured or any way sort of warped or any differences in picture. So that's what flat images are useful for. If you walk closer to the mirror surface, it's like your image is going to walk closer as well. You walk further away, it walks further away. When you put up your left hand, it may look like the image in the mirror surface is actually putting up its right hand, but in fact, that's actually just a mirror image of your left hand. Right? It's still your left hand, even though it sort of looks suddenly like your right. So it's just our brain playing tricks on us here. A couple sort of language we've been introducing here. We say objects are real, right? Because there's actual light rays pass through. So especially as we get to our curved mirrors again, whenever we have real images, you can actually put up a screen and you can actually project, because it is a real image, because there's real light rays that actually intersect at that point, you can actually put up a screen to actually get a nice copy of whatever you're imaging, a candle, whatever light source. Images in general are going to be virtual. We will see some examples of real images every now and then, but most images are going to be virtual. It's just our brain playing tricks on us here. I'm going to make that note again. Our brain interprets a straight light ray from, let's say, inside the mirror, or you can say behind the mirror, inside the mirror. So it's just our brain playing tricks on us here. Realistically, all the light rays are actually stuck on this side. Maybe you have a wall that's this mirror is fixed up to. There's definitely nothing sort of behind that wall there. But in this case here, a virtual light ray, it's our brain playing tricks on us here. It's where similarly the ray diagrams where they intersect, but because it isn't real light rays, the light rays are sort of stuck on this side, we can't actually project it on any screen. Virtual, so So it's intersection with, let's just call them fake light rays. Right? Light rays don't actually intersect there. It just looks like it had come from there, and therefore we cannot project onto screen. You can't put a screen, a sort of a blank canvas here inside the shininess of the mirror because you can't reach into the mirror anyway. So you can't project on the screen. As we'll see with lenses, there will be some images you can project. So those are real. The images that you cannot are therefore called virtual. So that's introducing some of the terminology for us here. We then took a look at curved mirrors. So let's just say curved mirrors. Did I say A? Yeah. Okay. So curved mirrors. I want to actually start off with the language of converging or diverging because we're going to do the same sort of separation for lenses. So we are still talking about a mirror. Let's start off with the converging mirror. Converging, as we mentioned here, is the light rays end up coming together. They end up squeezing closer to each other. The converging shape for a mirror is actually a concave mirror. So we've done a couple examples of this here. You may have a candle, right? We have a principal axis. I have a curved mirror. I'm looking at the opening of a cave, so sort of the opening is pointed towards me. This one we had, imagining that this mirror here ends up making a perfect circle. The center of that circle would be called the center of curvature. The focal point is always half the center of curvature. So focal point is half the curvature. And what we end up drawing, realistically, there's actually many light rays going in many different directions, so it gets a little bit complicated. We just decide to do for a ray diagram, just let me just allude to it again. A parallel ray goes through F, right? It focuses there. So using a ruler here, you do a flat ray there. It's just going to go focuses through that F point. We call this the focal length. It's the distance between the F and the vertex here. For this one here, wherever the rays intersect, the other ray we're going to draw is the one that sort of hits the mirror head on. That's the one that actually goes through the center of curvature, assuming that it does end up hitting the mirror somewhere here. It's going to hit at a perfect 90 degrees to the surface. We measure angles as relative to the normal, so it's 0 degrees in, 0 degrees out. We're going to end up getting light ray coming directly back the way it came. So 2, a ray through C is undeviated. It doesn't deviate to the left or the right, it just comes directly back. Where these two intersect, in this case here you'll notice it's real light rays that are actually bouncing off. They're intersecting on the real side of the mirror, which means if you put up a screen, it could be as simple as a piece of paper here, you're going to actually get a nice clear picture of your candle that's imaged on the screen here. If you move your screen around here, you move it left, you move it right, you may have light rays. They sort of strike the paper here, but they're not really converging nicely. You're just going to get a slightly blurry image. Some of them haven't quite made it yet. Some of them are already there. We'll only get a perfect nice image here. That's going to be real. And we're going to use the language here, real is positive. So in this case here, real is positive. And we actually have a positive focus, or positive focal length, because it's on the real side. It's on the actual side where the light rays are actually on. For mirrors, the real side is always the side where the object is on. The virtual side is quite clearly here. It's inside the mirror itself. We saw that in this case here. If you look up some of the details here, I'm not going to do it directly here. But in this case here, your image depends on your DO. And as you saw, is if you move your candle closer, this intersecting point, you're still going to draw the exact same two rays, but where they actually come together will actually change. Next time you look at a spoon, start out really far away, you'll probably see yourself as an upside down image. As you get closer and closer, you get right up to the spoon, you actually see yourself inside the spoon, you actually see yourself upright, and everything's nice and straight as well. Let me actually draw that while I have it on the diagram here. So we have maybe the same spoon that I'm looking at. The center is at some point, the focus is real, but let's say you stick your eye directly up close to the focus. Let's do exactly the same ray diagram. Let's do a straight line, a parallel fit. That's going to go through F. The other one that goes through C, undeviated here. Technically, it's actually hitting the mirror first, but then we're going to see a light ray here that's actually going through C. Make sure you use a ruler for this here. Hopefully you're able to see that with the ruler here, we're actually getting further and further apart on this side. It's never going to converge on this side. And yet here our brain plays tricks on us here. if we see a light ray having come with this straight line, it's like it had come virtually inside the mirror. On the other side, also virtually inside the mirror here. Again, you should use a ruler for all this here. And it therefore looks like we then have a image, but this one here is now a virtual image. This one here is we're looking at the shininess of the mirror surface, and it looks like we're larger. We can do definitions like, oh, it's magnified, it's bigger. We can still say it's upright because we're still right side up. I was pointing up. The candle is also pointing up. But because this is inside the shininess of the mirror, you cannot stick your screen directly inside. So virtual, it's just our brain playing tricks on us. We think that there's actually light rays doing that orientation. So this one definitely depends on DO. You don't need to memorize it. You just need to have out a ruler. Make sure you measure out F and C properly. The reason why you're not really seeing the deviations because right now my F is a little bit too far away. But make sure you use rulers for that. That's the case for a converging mirror. That's the case when the focal length is positive. Let's then switch over to what's called a diverging mirror. Whenever things diverge, it means light rays separate. So separate, they get farther apart. In the context of a mirror, the shape that I need to separate is actually a convex mirror. You cannot memorize. Convex is always diverge. You have to say convex for the mirror type is diverge. As we're going to switch over to lenses for today, we'll draw ray diagrams as well, but we're actually going to see the convex lens actually does converging. So just be careful. Lenses are the opposites of mirrors. So for a divergent case here, this one was a little bit easier. So we're still standing here. This time I'm looking at the bulgy surface of the spoon. This time, because the center of the circle is actually inside the shininess of the mirror, we still have a center of curvature, we still have an F that's halfway, but this one here, we're actually going to have a negative focus. Right? The real side is supposed to be the side that the object is on, this side is positive, anything internal in the mirror is now negative. So either they give me the focal length directly as negative, or if I know it's diverging and I know it's convex, I want to make sure I put in a negative for the F before I use the formulas. For this one here, the image doesn't depend on, so image does not depend on D naught. So again, the next time you look at a spoon, whether you're really far away from the bulgy side or closer, you're going to end up seeing the same image anyways. For this one here, we're going to do our ray diagram. Make sure you know how to draw ray diagrams for each of these devices. So this one here, we're going to draw a parallel ray, reflects as if through F, because that's the notion here. If I had a real light ray, if it was parallel, I would imagine it gone that way. That's not a real light ray because I can't be inside the mirror. But in the similar vein here, if I send in a real light ray, if this is a candle of some sort, it's sending a parallel light ray, where it would have intersected and kind of converged through F, it actually bounces off as if it leaves going through F. So maybe I should make this a dotted line here just to show you this is not a real light ray, this is just our brain playing tricks on us. The other one here is the one that goes through C. Again, using a ruler here, I want to aim for C. I want to target that center of curvature here. I would have been 0 degrees on, 0 degrees off, or perpendicular to the surface here. This ray here, realistically, actually gets undeviated. Here you can see the diverging a little bit better. It separates, but our brain plays tricks on us where these light rays here, if they had come in straight lines, where they would have intersected was actually, they would have intersected here. The image is always going to be upright. It's always going to be diminished. It's always going to be smaller, regardless of how close I walk to the mirror. So second ray here, a ray through C is undeviated or it's unchanged. It comes directly back, it bounces off. This is a virtual image. We'd expect a DI to actually be negative. You cannot project that on a screen. Right? So that's just a recap of what we did previous. What I want to do with you this lesson, just like before, I'm going to introduce to you lenses, specifically lenses that are curved. That's when we have converging and diverging. We'll talk about how to draw the ray diagrams, and then we'll switch over to simulation to see how this works. So now let's just put a big line here. We're now going to switch over to lenses as a new optical device. These could be similar to glasses. The key word here for lenses is actually refraction as opposed to reflection. So this one here, because light is supposed to get through your glasses, right? You don't want your glasses to sort of filter out all the light. We're actually going to have some of the same terms like DO, DI, height, object, magnification, all that the same. But this time we're actually expecting it to go through. So we're going to start off again with the two types of lenses here. You could technically do a sort of clear lens, a plain lens as well. Again, there's basically nothing, there's no curving, there's no changes to the image. I'm just going to skip that for now. we're going to skip right to the curved lenses. So just like we did earlier, I'm going to use the notion for a curved lens. We're going to start off with the notion of what's called a converging lens. Right? Converging again means comes together. The shape that I'm looking for a converging lens here is actually, this time is actually going to be a convex lens. Sometimes they even call it a biconvex lens. So let me just talk about what that means here. So earlier we said convex for mirror was actually a diverging one. Here convex for lens is actually a converging. It actually makes light rays come together. This is fairly easy to verify experimentally here. We're going to still have on our ray diagrams, we're going to still have a principal axis. Right, so some of the same terms here. Principal axis, you're going to still be the object. This time your lens, I'm going to put a sort of dotted line to it. Your lens, truly speaking, is going to have some thickness. But what we're going to pretend is we're going to pretend that the thickness is very minimal. Because what would happen realistically, if I wanted to have a convex lens, I want to have the bulge sort of point out towards me. I could have a convex lens here that's just sort of flat like that, flat on one side and curvy on the other. Just to dramatize the effect though, usually we do a convex on both sides. We do a curve on that side and a curve on this side. Technically speaking, the curve can be different. The curvature on one side can be different from the other one. They play around with that for glasses. Again, for simplicity here, we're going to pretend that they're the same on both sides. It's biconvex because you have two. Realistically, what's going to happen is the light rays, I'm going to draw a ray diagram in a second here. The light rays here that are going to intersect with this lens here, when they actually encounter this medium, they're going from, say, air into the glass of the lens here. They would actually refract, they would actually bend, they would travel straight through the lens here. As they leave, they would then sort of refract again, right? Realistically, they would actually refract twice. So that's actually what's happening. It just gets to be a little more complicated when we actually do a ray diagram. So what we're going to pretend is, yeah, let's pretend the curvature is the same. So let me actually write this down here. Assume same curvature, the same curve, the same shape on both sides. And assume that we have a very thin lens. And just for an approximation for a thin lens here, realistically it is hitting two parts here, but what I'm going to pretend is instead of our real lens looking like that, I'm going to have our principal axis, I'm going to have a dotted line, and that's going to be a sort of infinitely thin lens. We're assuming a lens is it's still able to keep its curvature, still the same shape to it, but it's so thin that when I draw these ray diagrams here, I would just imagine the light ray here is going to just intersect with the lens here once. And in this case here, because it's converging, I expect it actually comes together. Realistically, again, there's going to be light rays that actually go in every which way. Basically, there's many different light rays. We need to draw two particular light rays to figure out where do these light points here pass by, and then where they actually intersect. Do we get a real image or a virtual image? So in this case here, although I would call your DO will still be positive because I'm still a real person, right? Maybe it's a candle, it's emitting a real light source. This time, because I'm expecting the light to actually pass through, this time the real side for a possible image, the real side of the image is actually on the opposite side. That was different for a mirror. For a mirror, my real light rays here can never actually enter the mirror surface. So my object side here and the image side here, if the intersection actually appears on my side, we call that real. This time for a lens, again for refraction, because I expect the light rays to actually go through, real is actually on the other side. Based on the curvature here, similarly, we're going to have what would have been called the center of curvature point. Usually because, which I don't know exactly the reason, but because center curvature is going to be twice the radius, usually they just say this is focus, and this one here, the center curvature is just twice the focus. Maybe because in the situation of a biconvex lens, we actually have a center of curvature on both sides, it's just easier to say one focus and one 2f on both sides. The focus is on these side because they're now on the real side for the lens. These focuses here are going to be positive. So when we do our equations on the next lesson here, make sure those are positive. If I have the f and the 2f on this side here, these are actually going to be negative. Okay. So you see, because refraction does something opposite of sort of reflection, everything else is sort of flipped around. So without further ado here, let's take a look here. Let's take a look at what's called the ray diagram. Let's draw those two rays here, see how they interact. Wherever they come together, that's actually where the image is going to show up. So let's start off here. We're going to have our infinitely thin lens. we're going to have a real focus, a 2f point, a negative focus, and a negative 2f point. And let's say I'm out here, or I put my candle out here. The object distance is going to be positive, right? We're going to send in, here are two rays that you need to draw. A parallel ray, very similar to a mirror. A parallel ray, this time, refracts, so it's not a reflection, it doesn't bounce back, but refracts through the positive focus. Right, we expect the light ray to get through. So if this were a candle here, I send in a parallel ray. Make sure you do this with a ruler, especially when you're working your worksheets here. Parallel ray here, this time instead of bouncing back and instead of coming back through this focus, it's actually going to go through the focus on the other side. That's a solid line because the real light ray actually gets through. I expect it to refract. I expect even with the two bends with the lens, I expect it to go straight through. I expect real to be on the other side. This time the light ray that gets undeviated, sort of the one that's corresponding to the one that went through the center curvature, this is actually one that goes through the vertex. In this case here, a ray through V. In a similar fashion, it cuts the vertex here at 0 degrees, so it's just going to cut directly through it. In this case here, a ray through V remains undeviated. It remains unchanged. So although there are tons of light rays coming off from this candle here, I'm going to draw a real light ray. If I use a ruler here and I intersect where I actually run into the vertex, that one there actually is undeviated. To actually tell where the image actually shows up, I needed to use a ruler. I need to make sure the f and the 2f's are all double each other, whatever. But just for comparison's sake here, again, where your real light rays here are actually intersecting, we actually have our image show up. Because there's actual light rays that are coming through this, and because this is the real side of the diagram, this is now going to be a real image. Real image, again, you can project it on a screen. So if I put a piece of paper up at this distance here, right, I can do this more accurately using a ruler, but if I put a piece of paper up here, I should see a perfectly projected reflection image of the candle. If I'm a little bit too close or too far away, the things haven't converged yet, I'm just getting a blurry image. That's actually what projectors do. They play around with sort of how far away you put the screen, so therefore you can actually get a clearer image. That's when they intersected. This one, similarly here, this image, wherever your image shows up, is actually going to depend on the object distance. So let's put this here. Image depends on your object distance. Your object distance is always going to be positive, so it's a little bit weird. We had said the positive side, I'm expecting positive to be on the right-hand side. We're going to see in our formula, well, your object is an actual candle. It can't suddenly be negative, or else that suddenly means it's virtual. So DO is always going to be a positive number. What I mean by image depends on the object distance, let's just get right up close to this lens here, and let's see what's going to happen. So we're going to, okay, perfect. So we have a new example. We have a principal axis, right? I'm going to assume a thin lens, so it only intersects once. I have my focus, I have my 2f, those are the negative. I have my focus, I have my 2f. Depending on which side I'm standing on, I expect the other side to be real. So just for simplicity, let's put me on this side here. This time, like that spoon analogy, I'm standing right up close. This time it's a lens. I'm going to draw the same two rays, see where they intersect, and that should be where your overall image appears. So what's going to happen here is I'm going to send in that parallel ray. Again, make sure you use a ruler. A parallel ray here is supposed to go through the F on the other side, no problem. It's supposed to go through the vertex, undeviated. It's going to cut through, no problem. You should be able to see these two rays here are on a diverging path. They're actually not going to get any closer together. Our brain plays tricks on us again here. Our brain will actually say, if I see a light ray coming in at that trajectory here, that light ray probably came from behind, and this light ray here also came from behind. So while there is going to be an intersection point, you'll notice this intersection point here is not a real light ray. The real light rays had gone to the other side, they were diverging. But our brain actually plays tricks on us here, and our brain says, well, where they would have intersected is actually on this side, even though we don't have the same problem with, oh, I can't get inside the shininess of the mirror. Because these are not real light rays, it's not an actual light ray that's actually going backwards, this is not a real image. This is on the virtual side, this is on the negative side. This one here is now a virtual image. You can make a note to yourself, it's because no real light rays intersect. It's actually just our brain playing tricks on us here. Sure, there is a light ray that actually heads in that direction, but what I'm saying is when the light ray actually heads to the other side, it sort of just looks like it had come from behind. What's nice, however, even though I can't sort of project it on the screen here, when I look through, let's say here's my eye, okay. When I look through this lens here and I look from this side, I'm going to look through the lens. Here's the object, right? The object is my candle, whatever. I'm going to actually see a magnified image that's upright. So people that are doing magnifying glasses, things like that, one way of doing it is they can try doing it with a convex lens on both sides. So this is typical design for a magnifying glass. There is another way of designing it as well with the other shape of lens, but this is definitely the more common way of designing it. So this one here would be a magnifying glass. Basically, it takes really small objects like ants and whatever, and you basically magnify them, and it blows up the picture. It looks like the ant is suddenly bigger. It's still oriented upright and everything. It's just the object is now larger. Lastly here, I've just defined for you here, the image depends on the object distance, right? When I get right up close to the lens, I can actually start using it as a magnifying glass. Let's finish off here with the diverging lens. So we had converging lens, so let's go diverging lens. A diverging lens here is actually going to be concave on both sides, so we can do a bi-concave lens. Sort of the same analysis. Let's pretend that the lens is really, really thin. Realistically, I actually only need one, so let's say principal axis. Realistically, I only need one concavity, so I'm looking at the opening here, although it's made out of glass here, so light rays are supposed to get through. It just dramatizes the effect here if I end up doing the curve on both sides. In fact, just some notation here, because I want it to assume that's uniformly thin, some worksheets will actually have sort of a double-headed arrow sort of pointing inwards. The inwards one here means this concave lens. The other one here would actually just be double-headed arrow going this way. So just some notation for you there. This one here, same idea. We're going to have a focus and a 2F point. Our vertex is still there. Focus, a 2F point. This one here, the image does not depend on DO, right? And you're going to see that when I do my ray diagram here. The ray diagram is drawing those two light rays, seeing where they intersect, and seeing whether it's a real image or a virtual image. Your ray diagram here for a biconvex lens, right? We're going to have a parallel ray. Parallel ray diverges. It sort of leaves as if through F on the same side. I'm going to give you a summary chart later on so you can be clear which light rays you end up drawing. So this one here, we're going to draw a parallel light ray. Because we're expecting the light rays to just separate after they hit the lens, this time they're going to leave as if they had come through F on this side. So dotted line, it doesn't actually bounce back. Well, to be sure, lenses, they're not 100% transparent, right? Sometimes there's going to be the odd scattering reflection, but definitely the real light ray, it's expected to go to the real side. It's expected to sort of bounce off that way. The other light ray here is simple, and it says, well, the light ray that goes through the vertex is undeviated. So ray through V is undeviated. It just continues onwards here. You can probably see really well from this diagram here. On the far side, because the light rays here actually diverge together, they're never going to come together on this side. Where they intersected is actually here. This is interesting because we actually have a real light ray, but it intersects with a virtual light ray because there aren't two real light rays that are intersecting. This one here is still a virtual image. It's still on the negative side. Try to just get you used to just different notation here. Negative DI, you can't project it on a screen. So again, it's just our brain playing tricks on us. When it sees, again, our eye is over here. When it sees a light ray actually having kind of separating off at that angle, it looks like light travels in straight lines. It looks like it had come from this image here. So that's a virtual image. Sort of some of the main points here was real for a lens because of refraction I expect it on the other side, with the exception of DO, which is always positive, and then virtual is actually on this side. If I have any intersection, they aren't real light rays, I can't project them, and I'm actually going to get negative distances, negative F or negative 2F, which is what they notate for center of curvature. I'm just going to show you a quick simulation here just so you can play around with this. So same idea, first thing starting off with the biconvex lens. So this is the one that dependent on object distance. We have our focus right now at -4. I'm standing on the 2F point. the vertex is at 0. We have the real focus positive 4, and then positive 8 on the other side. We do expect light rays to go through. You'll notice for these ray diagrams here, they're actually drawing 3 lines. We did the parallel, converges through the focus on the other side, through the vertex. This is a real image. So if I put up a piece of paper and I put up a screen, that's actually where it's going to show up. What I'm going to do is I'm going to move this object back and forth. For this type of lens, it depended on where your object distance is. So I'm going to pull my object back a little bit here. You can just see what's happening to the image. It's getting tinier and it's actually getting closer. What happens if I get closer? In this case here, what happens if I'm between the 2f and the f on my side here? It's actually going to get larger. So you see that the height of the object is actually 2.08, where the image is 2.31. As I get closer, you can see that more dramatized. It's the same ray that I'm drawing, but where they're actually intersecting, when you actually use a ruler, it actually gets bigger. When I'm actually on the focus, we'll see that parallel through focus and the undeviated one is perfectly parallel. This will never intersect before or after. There's no images, real or virtual. As I get right up close here, right, earlier you can't really even see it, but this is like that magnifying glass analogy here. If I'm standing sort of half the distance, right, really close to this one here, the real light rays parallel through the focus, undeviated, these ones here just separate, they diverge, but they look like, dotted line here, they look like they had come from a virtual focus. So if I was, my eye was over here, as I look at a real object, the image of it looks like it's inside the shininess of the lens, and the lens itself now has a bigger image, and as I get closer, it just gets smaller. So you can play around with that one there. For this one, I can switch a convex lens to a concave lens by switching the focus point. I believe I can just change where the focus is going to be. I can even change the curvature of the lens. I'll show you that more with the next lesson. But I can change this focus here, maybe this focus. I can change the focus closer. You'll see some difference with the curvature here. But what I can do is I can put the focus here on the other side. If I flip the focus, now the focus is here, is on the opposite side. The lens has flipped to a concave, and this time it actually doesn't care how far away I'm getting. Maybe I'll be taller so you can see it here. Let's move the focus a little bit farther away so you can see it better. And you can play around with the simulation somewhere here. Again, those 2 light rays that I did, this one here that's parallel, it's going to diverge as if it had come through the focus on my side. You'll notice when I was moving one in the focus, the other one was symmetrical. We're assuming that the curvature is the same on both sides. And this one, regardless of how close I get, we're always going to get a virtual image. It's always going to be upright, and it's always going to be diminished. It's always going to be a little bit tinier. This is not a real image because although there is one real light ray, we're just our brain playing tricks on us. It looked like that line that diverges had come from this intersection point. So play around with that simulation some more. I'll provide a summary for you, just a summary chart for you. So make sure you're comfortable with drawing these ray diagrams. Thanks, guys. Take care.